at like, I'm a college student at NUS, National University of Singapore. And my past experience in CP has been like around like 4 to 5 years. I went to the Olympiad of Informatics. If I don't know if you guys know about it. It's like a school students thing. And afterwards, I like tried for ICPC and like went to regionals in my first and second year, and in in my first year, and in second year I went to the World Finals. Yeah, that's pretty much my competitive programming experience. All right, so let's start our first session of complexity analysis. Like first we'll go through like the basic definition of complexity analysis, and then like the way I was thinking was like first we can cover some MCQs on the resources mentioned. I'll just share the MCQ resource here in case anyone did not see it. And afterwards, I have some questions of my own which we can discuss. I think they're good. Yep. So I've shared the MCQ thingy. All right. So now I'll share my screen with you guys. So yeah, you'll probably. Okay. I'm hoping everyone can see the screen. Yeah, cool. Thanks for that. Like just give me a heads up if my voice or anything is not clear, like on the chat, or just unmute yourself and like talk to me if you have any doubts, or if you think my voice or screen is buggy or something. Yeah. So I had these few questions. Like I don't think we need to discuss all of them. So okay, the basic idea of complexity analysis is that you are trying to count the number of steps of your algorithm. A rule of thumb, which like most people use in competitive, is you have around 10 to the power 8 steps per second. What that means is that you can roughly do 10 to the power 8 steps in a second. And like on most of the online judges, you'll get like 1 or 3 seconds. Like the time limit of the problem will be either 1 second or 3 seconds or like 5 seconds at most. So roughly you can do 3 into 10 to the power 8 or 5 into 10 to the power 8 operations. That's like the rough upper bound. So if your algorithm is going around 10 to the power 9 or 10 to the power 10, most likely that algorithm won't give you the like full points, because yeah, that thing just doesn't work. Okay, so we have this rule of thumb. Okay, so let's cover this first example, which is like pretty easy. Question 5. You have okay, ignore the syntactical issues. Like I think it's written in Python, but you can get the broad idea that you have a variable, like you have a function f, and you have this a variable, and like you loop I, and then you loop again I. So here the idea is that this is n, this is m, so the total thing is n plus m, right? A question just for everyone: what if we had a line here which said a plus equal I again? Would it be 2n plus m, or would it still be n plus m? Out of these two options, which one do you think would it be? Just like put in the chat here. Like what if we had another line? Yeah, so all right, fair enough. So all of you have like some ideas. In complexity analysis, we generally say it's still n plus m, because we don't want to consider the constants. So if you have a code, let's say the broad code looks something like this: for I goes 1 to n, and then we have some statements like which are basic arithmetic, and then we end. You generally say this is order n rather than saying this is order 7n. If let's say there are 7 statements here, it's just the simplicity that order n is like much simpler to analyze. Like calculating that it's on is much easier than saying it's O7n. So yeah, just ignore the constants that you get everywhere. Okay, that's a rule of thumb. So, sorry. Yep. So in this case, this was actually n plus m. Okay. Like in the variation also. Cool. I had some other questions also. Let me see. Question 7. Yeah. Sorry. Okay. So question 7, just go through the broad code. You're trying to find the sum of the elements that are above the diagonal. above the diagonal of a matrix, and you have this sum variable and you're just adding all the stuff to it. Look at the looping structure. It's going from 1 to n, and then j is going from I to n. So just in the comments, like anybody who can, like, I don't know, yeah, just try to get what the option would be, like what the correct option would be. Okay, so Sachin has like n square, and that's pretty much it. Yeah. I'll just show you the analysis, like the broad analysis. Like obviously, sometimes it's like after a while you'll get the hang of it, and it will become very obvious that why is it n square. But like for the first time, I'm just showing you how it works. So think about how many, like when I is equal to 1, how many times does j run? J runs from 1 to n. That is j runs n times, right? When I is 2, how many times does j run? It runs from 2 to n. That is, it runs n minus 1 times, right? So if you think about it, how many times does this statement gets executed? Like the sum plus equal aij. How many times does it get executed? It's mainly n plus n minus 1 plus n minus 2 dot 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 up till 1, right? And this can be also written as so I don't know how many of you have like taken basic math courses or like high school maths. So basically this thing is like the expression for this is this thing, n into n plus 1 by 2, or yeah, n minus 1 by 2. I don't remember honestly. This becomes n square plus n by 2, which becomes n square by 2 plus n by 2. So actually it's around n square by 2. Like obviously, okay, again, another thing in complexity analysis, that if you have like a polynomial in n, let's say n square by 5 plus 7n plus 3 log n. Like obviously log n is not technically a polynomial in n, but just, okay, first ignore this. If you have something like this, you just say it's order n square. You just pick the highest power. That's it. Okay. Yeah, you just pick the highest power. And otherwise, if you have like something like 3 log n also, okay, anything to the power log n, so log n to the power alpha is generally considered smaller than n for any alpha. This is generally considered true for any alpha, like any positive alpha. So even like log n to the power 5. Although for practical purposes, it's not true, but like complexity analysis in itself is a theoretical subject. So anyways, this thing comes out to be n square by 2 plus n by 2. So we'll say it's order n square. Although if you want to be precise, you can say that we did n square steps here. Sorry, n square by 2 steps here, if you want to be precise. But like it doesn't matter. Like when you're doing complexity analysis for comparative programming, you're generally doing a hand wavy thing. You don't want to be very precise, so you don't really care about the constants. Okay. If anyone has any doubts, just like let me know. Okay. The next question I had was question 11. So this question is, yeah, you can read the function f of n. Firstly, does anyone have any ideas what is answer trying to print here? What is the answer trying to print? Yeah, the complexity analysis is log n. Like other player and Sidhant Bansal both are correct. Yeah. What is answer trying to print here? Just try to think of that. Roughly. It's adding n, then it's adding n by 2, then it's adding n by 4. Right? So answer is like somewhat looking like n plus n by 2 plus n by 4 dot 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 dot. So it'll roughly be 2n. Like I'm not sure, like if n is a power of 2, then it definitely will be 2n. Otherwise, it might be something else, right? We don't really care about what answer is, just a curiosity question. The number of iterations this code takes is basically how many times can you keep on dividing n till the time it hits 0. So if you start with, let's say, n equal 10, then you can divide it once, 5. You can divide it again, 2. You can divide it again, 1. You can divide it again, 0. And that's it. Like then it'll terminate. So in general, if you have n, so how it comes out to be log n is, you don't have to memorize this. The idea is like, okay, after the first iteration, it becomes n by 2. After the second iteration, it becomes n by 2 square. After the third iteration, it becomes n by 2 to the cube. Generically speaking, after the xth iteration, it will become n by 2 to the x, right? So when does n by 2 to the x hits 1? You want to solve this equation, basically. And this comes out to be n is equal to 2 to the x. Then you take log both sides. So x is equal to log n base 2. So like, obviously, intuitively, you can easily think Okay, Nikita is here. Can you summarize what is done? Yeah. So Mohammed is correct. We are reviewing some MCQs on complexity analysis, and like I gave the broad definition of complexity analysis as being the number of steps that are involved, and the tricks that are there are that you ignore the lower powers of a polynomial. Example here, we had n square plus by 5 plus 7n, and we ignored the 5 constant and the 7n itself. So it just came out to be n square. And the another thing that we are just now discussing is how do we get log n? Like obviously, people will get a very quick intuition after some time that why does like keep on dividing a thing by a constant. Let's say, okay, let's say a variation we have here. Let's say we have n and we are constantly dividing it by 1.5. Right? In how many steps will this end, do you think? Any answers in the comments? Like for this thing, people were correct that it terminates in log n base 2 steps. Yeah, so that is correct. Log n base 1.5. And like to be precise, if you have any constant here that's bigger than like if you have n by alpha, then n by alpha square, so on, going on. And if alpha itself is greater than 1, then this thing will terminate pretty fast. It will be log n base alpha, which is like always fast. Like if alpha is 2 or 3 or 5, then it's pretty good. It'll be pretty fast. Like log n base 2, log n base 5 or whatever. And even if it's between 1 to 2, it's like you won't see any practical application of this, but it's generally fast. But like the derivation idea, there are two ideas. So one is how many times can you keep on dividing from n, and that's log n times. The other is this more mathematical way that you see after how many iterations will it become 1. So you try to solve this equation and you get x should be log n, right? Okay. If I'm going too fast or something, please let me know in the comments. Okay, question 13. I feel this one is a nice one. Yeah, question 13. So you have answer variable. Let's not care about what the answer comes out to be at the end. What should be the complexity analysis? Any ideas? Or even if someone wants to unmute themselves and like give a broad description of what they think, how they approach this question, they can. Like if they know the answer. Okay, so yeah, two people said m log n is the answer, which is correct. Yeah. The analysis is slightly hard for this one. I feel like it's not that trivial. Okay, and you can like you guys can message on everyone. Like I think Mawsum messaged just me, but like yeah, you can just message to everyone. Like there's a to everyone option. There's no need to go and fetch that. Yeah. Okay. So the broad idea is that like n is going from n to n by 2 to n by 4, right? Up till 1, say. This is the I loop. And J loop is going from M to I, but obviously you can like, just for the complexity analysis, you can think of it from going from I to M. It doesn't matter. It's just simpler to think. Like it goes in ascending order, simpler to think than it goes in descending order. Okay. Now think about this. What if this was M to 1? If this was M to 1, this code would strictly be slower than the previous code, right? Because you'll have more iterations. Like M to I will obviously be faster because I is going to be greater equal 1, right? So if you analyze this code, when it goes from M to 1, it's easy to see that it's M log n, because in each iteration, we are saying that J goes from M to 1. So like J basically takes order M time. So J loop takes order M time. And in the outer loop, like how many times is the outer loop running? It's running log n times. So we say it's like the total thing is running M log n times. If you want a more precise analysis where you say that it's actually not going till 1, it's actually going till I. Okay, so what we did here was we showed an upper bound. We showed that this algorithm is strictly better than M log n. Like it can't go bad than M log n. Maybe it's better. Maybe it's order M actually, because we made this hack of changing it to 1, which is like technically not correct. So it might be order M or something faster than M log n, but we know at least it's not worse than M log n, which is important. Like sometimes you don't want to analyze the complexity of a very complicated thing. So you just say, simplify it and like try to analyze a worse algorithm, a bad algorithm comparatively. So in this case, if you try to like analyze the actual algorithm itself, it's slightly complicated, but like I think you can get it done. The idea is that j is going from I to m. So j will go from 1 to m in the last iteration. It will go from 2 to m in the second last iteration. It will go from 4 to m in the third last iteration, and so on. It will go from 2 to the log n to m in the first iteration. That's the idea. Okay, when it is a nested loop, we multiply the time complexity every time. No, okay, that's a good question, Shachutek. Here we could just multiply because I and j were independent. Like j, like, okay, when I change this code and say that this goes from m to 1, the j loop itself is independent of the I loop, in the sense that whatever the value of I is, it doesn't matter how many times j will run. J will run om times independent of what I is. Even if I is 5 or I is 7, you don't care. This loop will still run like m times, right? If it goes from m to 1. So in that case, you can just multiply nested loops. But when it's not going till 1, it's going till I, you actually care about the value of I. Okay, that's a good question. So in this case, like j goes like this, right? And if you try to sum this up, it's basically saying m minus 2 to the I goes from 1 to log n. You're basically trying to calculate this summation. Like that's how many times j runs, right? This is the entire total number of steps. If you try to solve this, I think this will still come out to be m log n, because the outer thing comes out to be m log n. And in the minus, you have 2 to the I going from 1 to log n. And this thing will come out to be 2 to the log n plus 1. So m log n minus 2 to the log n plus 1, which will come out to be m log n minus n plus 1, something of that sort. Like I think minus 2n. Yeah, so m log n minus 2n, but again, minus, like this term is strictly worse, so you can just ignore it. Any doubts in this question? It's slightly complicated, but like I think the key takeaway was that sometimes you can change some part of the code and just see like how will the worse algorithm, comparatively worse algorithm, perform. Okay, so Subham has a doubt. Suppose we have two nested loops, one having n square and the other having n log n. Then would the overall complexity be n square? Okay, I don't really get your doubt, Subham. Like, are you saying that the outer loop I runs from I1 to n square and j runs from 1 to, say, n log n, and some statement is executed here? If that is the case, then this entire thing will run n cube log n times, right? Like just multiply both the things. If you meant something else, then I don't know. You can clarify it by unmuting yourself if you meant something else. Or just like put another message on the chat. Yeah. Okay. So in case anyone has any doubts, please ask. Like, because like if you're seeing this thing like complexity analysis for the first time, this can get a bit like it's slightly mathy. Like sometimes you have to do summations and everything. So like maybe some step is not clear. Like expansion once again, please. Okay, which expansion? I did not understand for j equal m to I. Okay, let's see. Okay, this part, we'll just like quickly go through this part again. So for this question, the answer comes out to be m log n. And the idea was that, so, okay, let's say you have this code, which is for I goes from 1 to n and for j goes from 1 to I. Okay, this is another problem. Let's think about this one first. And this is obviously nested, and then some execution statement here. This like the complexity of this thing is n square, right? Because the number of steps is n square by 2. What if you change this thing to n? That is, j now goes from 1 to n instead of 1 to I. So you made the algorithm strictly slower than the previous algorithm. The previous algorithm was, let's say, algorithm A. The new algorithm is algorithm B. And in algorithm B, the only change is that we changed this j goes from 1 to I to j goes from 1 to n. Now this algorithm is definitely slower, but it's easier to analyze this. You can just do the multiplication thingy, n into n square, right? And if you go back to I, you know that this thing is strictly less than equal n square. That's the idea of like just changing the m to I to m to 1. Okay, the expansion once again from last series one. Okay, I can show. So if you don't change from like m to I to m to 1 and you still want to analyze this thing itself, it's slightly hard because there is a math involved. And here I'm trying to show the math. So in the first, like in the last iteration of I, think when I is 1. When I will be 1, J will run M times, 1 to M, right? When I will be 2, J will run from 2 to M. When I will be 4, J will run from 4 to M, and so on. So you're trying to sum up all these things, which is basically this summation that, like, okay, 1 to M is basically saying M minus 1 steps, 2 to M is basically saying M minus 2 steps, 4 to M is basically saying M minus 4 steps, and so on. So you're trying to do this summation, which is M minus 2 to the power I, and summing over from I is equal to 1 to log. You can open the sum easily, like this thing goes out in one sum, so it becomes M log N, and the other thing goes out like this is actually 2 to the power I. And yeah, you can try to work it out. It'll come out to be something like M log N minus 2N plus 1. And you can just ignore this part. So the result is M log N. So you mean you can tweak the loop to run the worst case and solve the complexity? Kind of, like not always. Okay, so the idea is if you tweak the loop and reach the worst case, analyzing the worst case is hard. So you can at least be sure that like your algorithm is definitely better than that worst case. But it might be the case that your algorithm is actually much better. Let's say here this was, instead of going from 1 to I, this was going from 1 to square root I, right? And then you just said like, oh, let's change this to N. Then obviously this thing is fucking slow. This thing is N square. But it might be the case that one, like J when goes from 1 to square root I, it might be the case that this thing comes out to be N root N or something. It might be the case, I'm not sure. But so when you do the worst case analysis, it's more like, if you know that the problem, like let's say the constraint on N in the problem is 1000, sorry. Yeah, let's say the constraint on the problem is N is 1000. Then doing this is all right, because you know that, okay, it's still going to be faster than N square. And I anyways know that 1000 whole square works on like most online judges. 10 to the power 6 works, right? Okay, so Subham has code. I goes from 1 to N, J goes from 1 to N something for this N square, and this is N square. So if a code has these total 4 loops, will the total time complexity be N to the power 4 or N square? Okay, it'll be N square only. Yeah, okay, good question. I think I didn't clarify it enough, but like in the early parts here, question 5, we did try to clarify this. So the idea was that you have some out, like something going, and then like if you have like some piece of code which takes some time, let's say T of N, and then below it there is some piece of code that takes F of N, then the total time complexity will be T of N plus F of N. Yeah. So if this is taking, let's say, N square times, and this is taking N square time, this will be N square plus N square, which is actually 2N square, but you can ignore the constant. So you can just say that in complexity notation, it's order N square. Okay. Any doubts? Okay, let's go to question 20 first. I think 17 is the hard one. I wanted to do question 17 and 20 first. Yeah. 17 I think was slightly, yeah, 17 can be like given a reference or something. I don't know. Okay, question 20. So like I'm not covering all the questions because I think only these questions are like quite good, like the ones that I'm covering right now. I went through all of them. So here you have a function f. It takes in an array A. Like just don't care about the syntax. Just know that small a is an array. Small a is an array. Okay, ignore the Python syntax. And n is the length of the array. And then you have this code running. How much time in worst case can this code take? Okay, so we have some people saying n square, some people saying n. Let's see more people answering first. Yeah, like just give it a minute or two and like try to think about what the complexity should be. And like just put it on the chat. Okay, so I guess we have a lot more people saying order n rather than n square. And like, yeah, that's the correct one. I'll just briefly go through the idea. So, okay, this kind of lays down the foundation of amortized algorithms. And like amortized is basically, they are slightly trickier to understand. I'll give you one example, like one very good example after this. But this one takes order in because, okay, like it might look like it's taking n square because you see two nested loops. One is going like this I1 and this J1. But the thing is, J never decreases. Like if you just think about the two variables I and J, like, okay, obviously saying what we want to say is how many times does this statement run? And it's actually order n times. The reasoning is that, think about this. When J, okay, let's say when I is 0 and this condition, like this while statement gets executed. Okay, Mohammed is correct. You don't know anything about the array A. Just think about the worst case. Like independent of array A, what if I give you the worst array possible? Then what will be the complexity? Here, when we are trying to analyze this particular question, we are trying to analyze it in this sense. That given the worst array possible, what will be the worst time complexity? Obviously, the best time complexity could be that the J thing never runs, right? Like that could be potentially the best, but like we are thinking about the worst case. So when I is 0, it might happen that J goes from 0 to, let's say, 5. I'm just giving an example. Now when I goes to 1, J will start running from 5 and let's say it runs till 6. All right. Now when I is 2, let's say J will start running from 6 and let's say it runs till 8 or something of that sort. Notice that J can't ever go back in this entire code. Like you only do a J plus equal 1 here and you never allow J to go back, like to get a smaller value than previously. So if you just try to see here, like when I goes to n, maybe J goes from n minus 5 to n. Let's say that's how this like structure looks like when a certain array A is given. Then how many times is J incremented? J is only incremented n times. So this statement only runs actually n times. Think about it. If this statement actually ran n square times, that means J had the value n square in it, which is not possible because this condition is there while J is less than n. And like intuitively, if you want to think about it, you can think about it like, obviously this is like the more mathematical way that I showed earlier. You can think about it like this. Given an array, I and J first are both starting here. In each iteration, I is moving ahead, right? And J is kind of sliding to the right. J can never go back left. Yeah, because J never goes back to 0. And more precisely, J never goes left. Like it can't even get a decrement or 2 decrements or 5 decrements on it in any step. So J will always go to the right. And how many steps can it take to the right if the array is of size n? It can only take n steps. Similarly, I is also only taking n steps. That's why the entire algorithm is order n. All right. This is slightly tricky, but I hope you guys like just try to count, like take an array and try to count how many times does this line run. J plus equal 1. Okay, Subham is asking why do we only calculate the time complexity in the upper bound sense? All right, and Chirag also has a question. Okay, so let's first tackle Chirag's question. I think that's more interesting. If instead of and we had an or here, what would happen? Let's see. Okay, I don't think it will still matter. It'll still, okay. While J is less than N or AI is less than AJ, let's think. Okay, if you have an or, then technically, even if one of the conditions is true, you can go, right? So the thing now that will matter is, before addressing that, okay, sure. Okay, so Chirag has this question that what happens when this loop has like this and is changed to or, which is a pretty good question, I feel. So if array A, okay, like I don't know how Python works, and like can you access the n plus 1th element in Python or not? Can you do a n plus 1 when there are only n elements? So that's one doubt that I have. I don't know how it works. But the interesting thing would be, let's think that J takes the value n plus 1. Then this condition will be false, right? Because J won't be less than n, it will be n plus 1. But this condition might be true. Like in C++, it might be true because it might be the case that your array is actually declared till like a very big size. And you can actually access the n plus 1th element, which is, let's say, by default 0 or something. Then it might be the case that this thing actually works worse. And okay, but it still would be bounded by the time complexity of the length of the array. Like whatever the declared length of the array is. Right? Does everyone get this? So when it's or, I think it still should be order n, assuming that the array is of size n and not of size let's say n square or 2n or 5. Okay. Another thing here is that there was this question by Subham, which was saying that, yes, Sachin is right. It may result in an index out of bound problem. Yeah. But most like, yeah, like there's a high chance that it will give a runtime error because of the OR condition, because this condition will be false, but it'll still go on checking the second condition, which is AI less than AJ, and it'll go in a runtime. That's true. Yeah. So Subham had this question that why do we only calculate the upper bound complexities always, and why don't we calculate the lower bounds or the omega? Okay. So just a brief note here about what he means. A lower bound generally means how fast can the algorithm run in the most optimal scenario also. Example, if you take the code of, let's say, some kind of sorting algorithm, let's say insertion sort or something, in worst case, they generally run order n square. That is, they take n square steps. But in the best case, they run in n. That is, they don't require more than n steps. We generally don't consider the best case because, like, as a comparative programmer, your target is to like get all the test cases correct on a certain problem. So, and you always assume that the problem setter is as evil as possible. That is, he won't set easy test cases. So he'll try to hit the worst case of your algorithm. You always assume that. Obviously, there are cases when the problem setter actually has weak test data and like suboptimal algorithms pass. But in general, you always care about the worst case time complexity of algorithm because you assume that the worst case would be present in the test data of the problem. So you don't really care about the best case. Like even if the best case is pretty good, you know that the problem setter probably won't test that. Like the test cases probably doesn't have the best case scenario. Or even if there is one scenario that's the worst case, you can't help it. So I think that's all the questions that I had. Apart from this, I had question 17 in mind. So like you guys can try to go through this question. Okay, the code here is not complete. Yeah. So this is a PDF thingy. I think there was like this X and there was this. I think there was. I don't remember. I think there was this mid and high here. Yeah, I think that's how the code looked. Like we are not going to cover this here because I think like we haven't covered topics like. Yeah, Mohammed is correct. Like data. Yeah, so he says that in the real world, data is generally huge, and like the worst case is usually the actual case. That's partially correct. Yeah, and like at least in comparative, you don't really care. Like obviously, and I've seen people caring about omega complexity and other complexities in randomized algorithms or like some algorithms where you know that the data that you get is quite noisy and you won't reach the worst case. But in comparative programming, we generally assume that the author will set the worst case. So for question 17, you guys can try to go through it in your like maybe at your home or whatever, or like some weeks later, because this has like some portions of recursion and some portions of binary search in it. So I don't want to go through the entire thing. But yeah, but I think it's a pretty good question because like the good part comes from the fact that like in the code, sometimes you're just calling one recursion when you're doing return this thing. But otherwise, if both of these conditions fail, you're calling two recursive calls, this one and this one. So like analyzing this is not obvious that like, because sometimes it's kind of like saying that f of n sometimes calls blah, blah, blah. It calls f of n minus 1. At other times, it calls f of n minus 2. And sometimes it calls f of n minus 1 plus f of n minus 2. So it's not really obvious how slow the algorithm will run because you don't really know when will it reach this condition, when will it reach this condition, when will it reach this condition. Right? But yeah, like just think about this problem as a homework or something. Like you don't intend to cover it right now. Okay. Could you explain O1? Okay, that's a good question actually. Ayush says, could you please explain O1? I think the broad idea behind O1 is that anything which runs in a constant time. So if you have something like, let's say, int a is equal to 5 into 5 into 5 plus 30, int b is equal to a times, I don't know, 7 plus 20, something of like some statements like these, which are basically just declarative. You consider it O1 because you consider the multiplication operation O1, you consider the addition operation O1. That's why this entire thing is O1. If you're doing something like, let's say you're doing some powers, let's say you're doing int a is equal to pow 2 to the 10, then technically this is not O1. Like a lot of people sometimes say that this is O1. Okay, it's like, it's not like you won't probably get in trouble thinking it's O1, but it's actually like either it's order 10 or it's order log 10. Like either this thing is taking 10 steps because you're taking the 10th power of 2, or it's taking log at 10 steps if the power function is written smartly. Okay, Shashutek has a good question. He has like, as a beginner, I sometimes can solve problems, but it gives TLE. What time complexities can be used in such cases for n square or below than that? Okay, so I'll just give you a brief like layout that I use generally. If the problem has a constraint of n 10 to the 6, then I generally consider it either ON or n log n. That's it. I generally don't think anything slower than this can pass. If n is at most 10 to the power 6, if n is at most 10 to the power 5, I think, obviously, I think n log square n has a chance to pass. Like sometimes problems have this n log square n complexity. They have a chance to pass if the n is at most 10 to the power 5. If, okay, generally nobody gives you if n is 10 to the power 4, less than or equal to 10 to the power 4. Most problems don't have this constraint because it's a very tricky constraint, because fast n squares can pass, and obviously n log squares n's or n log n's can also pass. But like this thing is very tight. If someone gives you n is 10 to the power 4, you're not really sure whether 10 to the power 4, like whether n square will pass or not, because it might be the case that your n square has a high constant factor because you're doing a lot more multiplication than additions rather than some other guy. So maybe yours gets TLE, but some other guys passes. So most of the problem setters avoid giving this thing, personally speaking. And if you have n less than equal 1000, then it's generally n square or maybe n square log n. But yeah, that's the most common case of seeing an n square algorithm, like what Shashutek was asking. I think that's the most common case. And if n is less than equal, I think 300-ish, then we generally consider n cube also as a possibility. So Floyd-Warshall is like a graph algorithm, which is n cube. And like, I think there are very few algorithms which are actually n cube by default. But for those algorithms, generally the constraint is like n is either less than equal 300 or maybe n is less than equal 400. In those cases, n cube can pass. And I think if n is, I think the next obvious thing comes out, like if n is less than equal to 20, then 2 to the n passes. And I don't know, if n is less than equal 15, then n square times 2 to the n passes. Yeah, like I think that's the most common ones that people use. And maybe last one, if n is less than equal 10-ish, then n factorial passes. Yeah, like, I'm not really sure about the n less than equal 10, but I constantly use at least these, I guess. Like, I'm not saying that if n is less than equal 1000, it's definitely an n square algorithm. It's more like you can't go worse than n square. You can't go n cube. N cube won't work. Obviously, these are like rule of thumbs. Like, I think sometimes if the test data is set weak or something, then you can probably get it. Anyways, done. Okay, so Shashutek has another question. One more question. In each problem, we have t test cases done. It also gets added to time complexity. Yes, that's a good question. So most of the problems have like t test cases input. So whatever you are doing the analysis of, you just multiply it by t. You say t times whatever analysis I did. Okay. Other player has this question. When we get t is equal to 10 to the power 5 and n is 10 to the power 6, then how can we approach it? Yeah. Okay. So when generally t is 10 to the power 5, like that is you're getting 10 to the power 5 test cases, and in each test case n is less than equal to 10 to the power 6, it's generally expected, like the thing is probably O1. Like for each n, you're probably giving an O1 answer. Let's say the question is count the number of even numbers in the range L to R, and you're given t test cases. And in each test case, you're given L and R, and you have to count the even numbers in this range. So technically here, the value of L and R can be arbitrarily large, and t can be, let's say, 10 to the power 5. So I think this thing is generally expected to be done in O1 or like pretty fast, O log n or whatever in that case. And Krishna has this question: when n is greater than 10 to the 18, tell about the modulo 10 to the power 9+7. Okay, I'm not really sure what the question means. I mean, when n is generally greater than 10 to the power 18, the issue comes that you can't represent it as a long in C++. So representing that number itself is pretty hard. And if you want to modulo it, then you'll also have an issue. Okay, so Subham has a good question, but it's a very generic question. It's kind of like related to optimizing algorithms and looking like how to find whether a certain question is looking like a dynamic programming question or not. I think we'll cover this stuff later, Subham. So like you don't need to really think about this. Like we'll definitely cover some stuff like this. Like I have a plan of today at least showing my ID setup to you guys, because a lot of beginners sometimes have like, I don't know, slightly slow ID setups. By ID I basically mean where do you write your code and where do you compile it, and like how can you be slightly fast about it, because a lot of contests have this thing like you can't be like, you don't want to lose out on minutes because of having a slow setup. I'll cover that later, but like let's just first cover complexity analysis. So we got this good thing here that's like a basically rule of thumb, and apart from this we had some recursion thingy, and question 17 can be thought of by you guys later on, right? So I'll stop this screen share here and we can go to another screen. Okay, so can everyone see the Sublime text generator? Yeah, cool. All right. So here the idea is that okay, so I had these few questions prepared. Like we covered this thing already, right? We covered this. Okay, this is a basic algorithm which we also like just covered. Sidhant Madan has this question. What's the meaning of reducing the range by modulo? What's the meaning of reducing the range? I don't know what the question exactly means. Generally, the idea is that a certain question has like wants you to calculate something. Like why modulo is used, I can answer to that. That why do questions have this modulo thingy and why is it generally 10 to the power 9+7? The idea is that most questions want you to answer some big value. Like let's say there is some combinatorics question or some DP question, dynamic programming question. So the actual answer will probably be of the order 10 to the power 100 or 10 to the power 50. But C++ cannot store integers that big. But they still want to verify your answer. The online judge still wants to verify whether you got the correct thing or not. So they want you to modulo it some, like they want you to kind of keep it within a certain bound. That's why they use modulo. And the specific reason of why they use 10 to the power 9+7 is mainly because it's easy to write. It's not like some complicated 9-digit number that you can't remember easily. It's not like some number like this, right? It's easy to write and it's a prime number and it's very big. So had this number been like, had the prime been like something like, let's say 1003, something of this sort. I'm not sure if this is the prime or not, but let's say the prime was 1003. The issue would be that people would try to come up with solutions which exploits the fact that the answer can only be in the range 0 to 1002. So that's why they have such a big prime use. But yeah, okay. So we have this question first. Let's just label these questions. Question 1. Give the complexity of an algorithm which runs in n plus n by 2 plus n by 3 plus n by 4 ... up to n by n steps. Yeah. So any answers for this one? Like basically in the first iteration, it runs in n steps. In the second iteration, it runs n by 2 steps and so on. I can give a short code if you guys want. Okay, so I think Sidhant Bansal is correct. It goes from, let's say, I, and then J goes from, say, and then we are here doing like some print statement, blah, 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 right? So here we are, let's say, printing haha. So how many times is this haha statement printed? That's the question, right? Like this question is basically equivalent to this. So actually the answer is, okay, notice that here I have J plus equal I. So basically in the first iteration of I, this thing will run n times. Then next time it will run n by 2 times. Next time it will run n by 3 times, so on, right? So the answer is n log n. Most people are correct, right? The way it works out is if you try to work out the math, you have this expression n plus n by 2 plus n by 3 ... up to n by n. You can take out the n common. So in the bracket, you have 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 ... And this thing is a harmonic series. I don't want to get into the details of this, but this thing comes out to be something like log n plus 3 or log n plus 2. So this thing is n log n, that's why, like order n log n. Okay. I don't want to get into the details why this harmonic series converges to log n, but one way some people think about it is, I can just give you the idea. This is basically saying you're summing 1 upon I, where I goes from 1 to n, right? This is roughly equivalent to saying we are integrating 1 by I, where I goes from, I don't know, 1 to n. Okay. Now, obviously, there is a big hack here that how can you say summing is equal to integrating? I don't want to get into the depth of it, but like just so you know how people quickly come up with these like closed forms of these summations is this way. They say that it's equivalent to an integral. If you've done like 11th grade or 12th grade mathematics, you know what the integral of 1 by n is. It's basically log n. So here it will come out to be log x, going like where x goes, like x equals n. It's a definite integral, x equal n and x equal 1. So which will be log n minus log 1, which will be log n. And this thing works for other cases also. Like let's say we were summing 1 by I square. You can do the integration thingy. It most likely works. I can't give the why the justification is. I can't justify easily why the sum is equal to integration in this case. It's a hand wavy technique, but it's a fast way to get the idea of why this thing goes to log n. All right, any doubts here? Okay, I don't see any doubts. Yeah. If anyone has any doubts, just unmute yourself and ask the question or ask on the chat. I think I'm constantly trying to answer all the questions in the chat. Okay, anyways, this question then, question 2. It's basically, you have basically array, composite array is composite Boolean array, and you have a vector of primes. Just if you don't know what vectors are, just think of this like an array. Just think it's an array. If you don't know what vector is, okay. And then you have this command memset. Okay, anybody wants to tell other people what memset is if they know? What does memset do? I think it's a pretty good thing. Like a lot of people use it. Like I use it at least a lot. Initializes the memory. Yeah, so Mohammed is correct. It initializes the memory. So the broad syntax of memset is generally container name, value to put, and size of container. So here I'm saying I want to like initialize is composite container with the value 0 and till all the n values. If I did something like -5, then only the first n-5 values would be set to 0. All right. One important thing here to note is I've seen a lot of people do bugs like this. Let's say they want to set everything to 3. Will this work? Will this work? Okay, so Chirag has this question. What is the difference if we initialize the values using a for loop? Actually, there is no difference. Sometimes people claim that memset actually works faster. So there is a very close margin of calls that memset is slightly faster than an ordinary for loop, but it's just more convenient. Like why most people use it is it's because it's just more convenient. Okay, so Pranch said that it won't work. Pranch, do you know why this won't work? It's pretty tricky actually. Like I personally have got a lot of wrong answers because of this thing earlier on, and I've seen a lot of people make this kind of mistake. So just remember that this thing can only be 0 or -1 for most practical purposes. If you try to set it anything else, it might not work correctly. Okay, so Pradyum has this out. If at the time of declaring we do kind of this thing, then will it work? Yes, it generally works. I've seen a lot of people do this. I personally don't do it, so I can't comment much. But I've seen a lot of people do this thing. So it generally works. And another thing is that if the thing is present as a global array, it's always set to 0. If you declare any array globally, it's always set to 0. If you initialize it globally, not in the main, if you initialize it globally. So here we actually don't need to set it because this thing is anyways set globally. Like is composite is anyways set globally to 0. Yeah, it will work. So other player has this question that will this work? As far as I know, this works. And even if you remove this, it's by default set to 0. That's how global memory works. Mohammed asks, is this related to the fact that it's a bool array? No, I don't think so. Like, even if this was an integer array or a char array, this thing will by default be initialized to 0. So even if you put this or you don't put this, this will be initialized to 0 because it's in the global. Had it been in the main, then this thing obviously would be garbage. Like, you'll have a lot of garbage here. But if you do this, I still believe it sets it to 0. Although I haven't tested it out a lot, so I'm not sure because I know you. But like, yeah, you can probably test this out. But anyways, yes, that was a good question. So when you use memset, no other value works. Yeah, like you can't be sure if any other value works or not. So like if you look up on the syntax of memset, it's basically this thing comes out like something like 2's complement or something. I don't remember the exact detail, but if you put in any other value, it doesn't work as expected. It's only it only has a guaranteed behavior for 0 or -1. That's it. And obviously, because boolean is is composite is a boolean array, so you can't put -1 there. You can only put 0. Anyways, let's move on to the code. So you have this is basically sieve of Eratosthenes. I don't know how to pronounce this, to be honest. Eratosthenes, yeah. This is basically that code. Eventually in the primes you'll get, yeah, so someone mentioned the memset, yeah. So it's basically int char, and I don't think you like it basically is a function of a character array. For a character array, it's a string. It comes under the string header as far as I know. Yeah. In this code, yeah, this is basically sieve of Eratosthenes. The purpose is to list all primes less than equal n. Okay. And how slow is this algorithm? That's the question. Okay, I think I've made a bug here. Just give me a moment. If it's prime, then we, oh, sorry. Yeah, so there was a slight bug. Yeah, I think now it's fine. So I don't have syntax highlighting here because these are short codes. I don't know. If you guys want syntax highlighting, I can do that. I don't know. If there is any preference for syntax highlighting, or I can copy paste these codes on the chat, just so if you guys want to like manipulate them, then yeah, I think it's easier to read. And like maybe you can copy it on your own text editor or whatever. So here the question is, we are trying to come up with the complexity analysis of this thing. How slow is this thing? Anyone has any answers? I mean, obviously we can see that this is definitely faster than the previous thing that we saw, right? This thing, because here also the loop goes like j plus equal I, it jumps by I steps each time, but we are not trying for every I. For some I's, we just continue gets triggered for some I's. So this thing doesn't run always, right? This portion doesn't run always. So this algorithm is obviously strictly better than and dot dot dot, right? So that means it's strictly better than n log n. Now, is it like how much better is it than n log n? That's the question. Yeah, so I said that it's n log n. And yeah, Prince also said that it's n log n. Okay, yeah, so you're correct. So the analysis comes out by the fact that, okay, firstly, I'm not covering sieve of Eratosthenes here, probably because we'll cover it in some future lecture. Like the idea behind like why this thing works and like why do we get all the primes from it. Just know that this thing only runs if I is prime. For now, just black box that portion. If you don't understand sieve of Eratosthenes, it doesn't really matter right now. Just know that this portion here, the one that I'm indenting right now, sorry. Yeah, this portion here runs only when I is a prime. So that means when I is 1, this thing runs, right? Sorry, when I is 2, this thing runs. And how much time does this thing takes? N by 2 steps, right? And when I is 3, it again runs. And how many steps does it takes? This thing takes. It takes N by 3 steps, right? And when I is 4, does it run? No, it doesn't run because it's composite and we'll just continue. Now, when I is 5, it'll again run. So N by 5. And basically that's the summation. Basically, in the denominator, we only have prime numbers, dot, dot. So if you take out the n common, we get half plus 1/3 plus 1/5 plus 1/7, dot, dot, which comes out to be, it's equivalent to saying n times 1 by prime. Sum of primes. Sum of 1 by prime, where prime is like all the primes less than n. I don't remember offhand the proof of why this comes out to be log n. So basically, this thing or this thing, which is easier to see, 1/2 plus 1/3 plus 1/5 plus 1/7, this thing comes out to be log of log n. I don't really remember the proof. It's pretty much the only place where you will see log n, at least related to prime numbers. You won't ever see log n again, most likely. And the fascinating thing is that, like, for most people, this is around order 5n or something. So in comparative programming, we generally treat this to be pretty fast. So like for practical purposes, even if your n is as big as 10 to the 7th, you can do a sieve of Eratosthenes, because this thing doesn't grow fast at all. Like think about what log of 10 to the 7 would be. Log of 10 to the 7. So it'll be roughly, I don't know, log of 7 log 10, which will be roughly log of 21, which will be roughly 4, I guess, or 5. Yeah. Like obviously these are like approximates everywhere. Like, yeah. So that's why this thing runs pretty fast even for n 10 to the 7. Okay. And okay, I didn't cover basic properties of log, but I hope you guys know that. Log of a to the b is generally equal to b log a, and log of ab is equal to log a plus log b, and so on. Like if you haven't taken logarithms in like your high school or I don't know, university, you can probably Google it up, and like these are just some basic properties of log, which it helps if you know them. Yeah. Any doubts in this question? Or we can move forward. Okay, let's move forward. And like I don't think we have a lot. Yeah, it's 1 hour up roughly. Question 3. Okay, so this is a pretty long question. I'll give you guys some time to think about it. Like I'll just copy the code here. I ran this code on my PC and it works. So I shared it on the text chat for everyone. And what I'll do is I'll share my entire screen. And all right, so everyone can see the code, right? Just message on the chat if you can see the code here on the editor. Yeah, cool. Okay, so that's how my setup looks like, at least for competitive programming or in general. I use Vim editor. I can just put it Vim editor plus okay, and like so. And this is my RC file. So basically, Vim is a pretty good, powerful editor. If you just Google about it, you'll see like a lot of people use it. And it's fast in the sense that you don't move with your arrow keys. One example is that you don't use your mouse a lot. And you can do precise operations. Like example, you want to delete 3 lines from here. You can do, I'll press 3DD and I can delete 3 lines. So I just pressed 3DD and I could delete 3 lines. If I press U, I can undo. And yeah, it's a pretty old editor. It's actually, I think it's built in 1960s or something. So it's a pretty old editor and it's still quite far, like it's still quite efficient, I would say. And one of the benefits of using an editor like Vim or Nano or something of this sort is that you get it at most competitions, because most competitions have Linux machines, and in Linux machines, generally editors like, I can try to list here, Vim, Nano, Gedit, all these editors are by default installed in all Linux machines. So that's one of the benefits, that you don't have to rely that whether they'll provide me with this editor or not. Otherwise, like some people, I've had issues where people are like using dev C++ or something, and in some competitions, they might not have that particular IDE or editor. So you can like, okay, let's take a break for like 3 minutes. And like, I'm assuming everyone who would try to read this code, I can lay out some comments here just to so that people who don't know some stuff can see. So, okay, const are basically things that can't be changed, right? And okay, this particular thing basically means we are doing x and the and is the binary and operation 2 to the power pos. That's what we are doing, and we are testing whether this ANDed value is whether it's equal or not to 0. Okay. Another thing I think someone might ask me is that why does my not equal looks like this thing instead of this thing, right? That's mainly a font that I have. Yeah. Some people previously asked me that why does it look like this? I can give another example. If I do arrow this, then it looks like this instead of, yeah. If I do a backspace, it becomes like this. That's basically a font that I have on. Like it's independent of Vim. It's more like a terminal font thing. So it makes your thing look simpler. I don't recommend it or anything. It's just, yeah, it's not a special character that I'm using here. It's just a not equal only. That's what I want to say. Your font isn't very visible. When you take a break, can you please do on dark screen, white, bright font? Okay, sure. Okay, so I have firstly magnified my font, and yeah, so I think we are taking a break right now. I like this is the code. I've copied it on the chat also, and I've explained I think this part, right? I've explained this part that what does this basically entire thing does, and I can explain this part also. It basically flips the post bit of x. Okay, so how it flips how the flip works is basically you XOR it. So x XOR 2 to the pos. You do a XOR operation. And if you don't know about XOR operation or AND operation, I would recommend you to just Google them up right now. They're, I don't know, AND is at least pretty simple. XOR is slightly complicated, but I think you can get a hand of it quickly. So just like everyone can try to go through this code, which I've sent on the chat. Okay, yeah, fair enough. I can share the code on some other platform, so that will be more convenient actually. Okay, so I've shared the ID one code. Yeah. Yeah. Like it's I think it's a reasonably hard exercise. I don't like, yeah, don't be demotivated if you don't get it correctly. Let's start back. Yeah. Okay. So the answer is actually ON. The code is slightly tricky. So, okay. First, I'll try to explain what the idea of the code was. You have a counter variable. You're trying to increment it till the value n-1. Okay, that's pretty simple, right? And this is your increment function. The way you increment it is slightly complicated. So you take the binary representation of x and you try to like go from x to x plus 1, but in its binary representation, not like normal integer way. So you can see in my entire code, I'm never trying to do something like x equal x plus 1 or something like x plus plus. I'm never doing that, but still I'm incrementing, right? So the idea is, let's say if x is like in binary representation, it looks like this, let's say, okay? Then in the next iteration, I want it to look like this. And in the next iteration, I want it to look like this. All right. That's how it works, right? When you add plus 1 in the binary representation, this thing will change. And in the next binary representation, it will become like this. Okay, I'm not sure if like people know how addition in binary works, but like that's how carryover works basically. When you're adding a 1 here, the idea is that you are doing this thing, which makes it this, and then you're again doing this thing, and then like this thing gets carried over like normal math, like normal addition that we do in base 10, and the carryover stops when it reaches this position. Yeah. Okay. So the code looks basically as follows. You start from the least significant bit, that is 0, and you go till the most significant bit, right? So you go from left, right? Okay. In this portion, you go from right to left. Okay. And if the bit is on, then you know you have to flip it because there is a carryover coming, right? Like in this case, this bit is on, so we flip it because in the resulting x plus 1, we have to flip it, right? And then we flip this one, then we flip this one. So basically, we are constantly flipping all the rightmost consecutive ones. Whatever we encounter here, we encounter 3 consecutive ones. And then when we encounter the first 0, we flip that also, but we break immediately. That's how basically a plus 1 works. Okay, everyone gets the plus 1 part, right? Like how plus 1 in base 2 works. And why is it like you start from the right, you keep on flipping as many ones as you see, and then you flip the first 0 and you break. That's the idea. Flip ones starting from right. By right, I mean least significant bit, which is least significant bit, and then flip the first 0 you encounter, then break. That's the idea. All right. So the flip bit basically works like this. So this function is O1, right? Because you're just doing a XOR operation. This is O1. Similarly, the checking part, whether the bit is on or not, is also O1, right? Because you're just doing AND with this thing. And okay, construction of time taken to do this int y is equal to, this is O1. This is O1, whereas this is order pause or order log pause. Just know this, that bit shifting is actually considered fast. Bit shifting is considered order 1, but things like these, like using a power function, is generally considered slower. I'm not sure which one it is, but I think in C++ it's order pause. But yeah, if you write your own power function, you can make it as fast as order log pause. I won't go into the details of like why it can be log pause, but yeah, and here also. But this thing is O1. So this entire thing is also O1. And like checking with the and checking the equality, or this equality is also O1, right? So could you please tell us the name of the algorithm? I don't, for the log par. Oh, for the log par, people generally say it as binary exponentiation. Okay, yeah, binary exponentiation, basically. I think the like broad idea is if you have a to the b, you can write it as a to the b by 2 whole squared. If b is even, and a to the b is equal to a to the b minus 1 times a if b is odd. And you can keep on doing this recursively. That's the idea. So it terminates in log b steps. Yeah, so that's the idea of binary exponentiation. We don't care about this. The key thing was that these two functions are O1, so we don't care about them. So what we care about is how many times is this I loop run? Like till what step is this loop run? The I loop, right? How many, like obviously it doesn't go to login always because it breaks when it finds the first 0, right? So basically, like the complexity of this is kind of like position of first 0 in base 2 of x, kind, right? Like if the position of the first 0 is the very first place, then this is order 1. If it's at the third place, then this is roughly order 3. Like you take 3 operations basically. And if it's present at the 10th place, then it takes 10 operations, right? So you're doing this thing and you're doing it for all x's because you're calling increment for every x, right? Because it gets incremented each time. So the total complexity is equal to sum of position of first 0 in base 2 of x, and here we are summing x goes from 1 to n minus 1, right? We are trying to solve this thing, that like what are the positions of the first 0th bit in different x's, and what are the sum of those positions. Everyone gets what we are trying to solve here, and like why we are trying to solve this. I'll later show that this actually comes out to be order n. This will actually come out to be order n. But what I want to show is the complexity is actually this thing. Like that's the important part, right? Yeah, that's the first part at least on the question. Any doubts, you can just put it on the chat. Okay, so the way you go about it is, let's say n is 8, okay? Think about what will be the different values of x. So it will be 0, 0, 0, it will be 0, 0, 1, it will be 1, 0, 0, 0, 1, 0, then 0, 1, 1, then 1, 0, 0, then 1, 0, 1, then 1, 1, 0, then finally 1, 1, 1, right? Think like, okay, for simplicity, think that n is a power of 2. So it'll go through all these things, right? Now, okay, now see how many values of x are there in which the first bit is 0. For n equal 8, there are 4 values, right? Like this one, yeah, half of the values, yeah, and this one, and this one, and this one, yeah. Combinatorially, how will you solve this? So let's be slightly more generic. Let's say n is some 2 to the p, okay? And your x will, how will it look like? It will look like p dashes, right? It will look like these dashes. And in each dash, there will be either a 0 or a 1, right? In each dash, there will be a 0 or a 1. And you're trying to find the number of ways that this thing ends at a 0, right? So how many dashes do we have before it? We have p minus 1 dashes, correct? And how many ways are there to put any digit in each of the dash? So in a single digit, in a single dash, you can put 0 or 1. So you have 2 options. And you have p minus 1 such options, like p minus 1 such dashes. And for each dash, you have 2 options. So total number of options is 2 times 2 times 2 dot dot dot, which is equal to 2 to the power p minus 1. So there are 2 to the power p minus 1 ways such that the rightmost digit is a 0, correct? Now, how many ways are there in which the second rightmost digit is a 0, but the rightmost digit is a 1? Like basically these 2 positions are fixed. Then how many ways are there to put values here? Yeah, so Sachin is correct that it's basically now we are left with p minus 2 dashes. So it's 2 into 2 into 2 dot dot dot, but you only have 2 to the power p minus 2 dashes now in this case, right? Generically speaking, if you had something like this, then how many? 2, like basically in this case, you only have 2 dashes left, so 2 to the 2, right? Which is equal to 4, and so on. If you try to count the sum of all these things, the next one will be 2 to the p minus 3, and then so on. If we try to count the sum of all these things, we'll get the same value that we get from this expression. Is this step clear? This is like the slightly tricky step, that this expression is equivalent to summing up these values, all these values. Basically, I can write it once again here. This expression is equal to sum of 2 to the power p minus I, where I goes from, I don't know, 1 to p. Yeah, these both things are equivalent. Because in this one, we are trying to count the position of 0 for each x. Here, I'm just regrouping the x's. I'm saying, let's first count for only those x's which have the rightmost guy 0. Then let's count all for all those x's which have the rightmost guy as 1, but the second rightmost guy is 0. then count for a few more x's. I'm just regrouping the sum. Like the sum consisted of n terms. I'm just saying that let's break the n terms into different groups. First group is of this thing, like the first this thing. Second group is of this thing, and so on. And we have log n groups, right? So, okay, calculating this thing is easy. So, yeah. So when you have 2 to the 0 plus 2 to the 1 plus dot dot up to 2 to the p minus 1, this thing will basically come out to be 2 to the p minus 1, which you can approximate by saying it's almost 2 to the p, which is n, right? We wrote here n is 2 to the p. We were assuming n is a power of 2. So we are done. So this is order n. So this shows that you can't always do this multiplication thingy. Like here, the trivial analysis was that you say that, okay, this thing runs n times and this thing runs at most log n times. So it's at most n log n, which is correct. It is at most n log n, but if you do the analysis more carefully, you can get a better bound. So yeah, so saying that this algorithm is order n log n is not incorrect. It's just incomplete information. When you say it's order n log n, you're saying that this algorithm runs faster than n log n, which is correct. It runs like less than equal to n log n, more like, right? But you can also say that it's order n because it runs less than equal or faster than n also. You can't say that it's order square root n. You can't say this. This is wrong because it doesn't run faster than square root n always. It should run faster than square root n always if you want to say that. So yeah, I mean, that's just the confusing part. But the main idea was that you don't always calculate complexity by just saying multiply this thing with this thing. Like just multiply both the thing, both the nested loops. But instead, you sometimes have to work out the math to get a more precise answer. And like almost all the math that you get in these kinds of questions involves geometric series or some kind of mathematical induction. But like, yeah, so you should be pretty familiar with how to do sum of GPs. Like this was a sum of geometric progression. And regrouping the terms into different groups is a common technique when you do analysis. Like if you think the calculating this thing is complicated, you try to find a way to regroup it such that it's simpler. So this is a way of regrouping it. Any doubts in this? This is like slightly confusing. Like it was a hard question. That's all right. So let's move forward. I think like everyone is. I don't see any doubts. Yeah, on this one. Yeah. Okay. We can find that moment. Sure. So this was the question. Okay. I'll leave this question. Yeah. First, let's see this question. Yeah. Just leave this question. Like, okay, this was question 3, question 4, question 5, question 6. Okay. So I'll leave question 4 and question 6 on what mathematics topics a C programmer should have a good command. Either player. Okay, good question. I feel. I'll just. So in general, like with people when I talk, I think most people say combinatorics, which is basically permutation, combination, binomial theorem, basic probability, and stuff like this. I think Aristo has a pretty good blog on this. So Aristo's a like pretty strong programmer on CodeForces, and he does a lot of live streams and blogs, and he has this blog on expectation, probability, expectation, and stuff like that. Geometric series. Like you don't really need to be good at calculus or things like that. You need to be more good at discrete things, which is I would say combinatorics is probably the most important thing. Okay, yeah, modular arithmetic too. Yeah, so I think his handle is Aristo, and I think his real name is Kamil Debosky. I might misspell his name, but he's read on CodeForces, and like I think he's a pretty strong programmer in general, and like he has a YouTube live stream and he discusses some math also. So like, yeah, you can look up and like I think he has good advice on these things. Okay, so we have question 4, 5, 6. I'll definitely say that question 6 is a homework because it's pretty hard and I like don't want to get into the details. And like you guys can try it later if you want. And I'll just relabel them as question 5, question 4. Let's go through question 4 and see how much time we have. We'll probably skip both these questions. I can copy paste them on the chat if you want to give them time. Okay, I'll explain question 5 in more clarity, but question 6 simply means, let's say we have this function f of n is equal to square root n, okay? And you keep on applying this function again and again. So we denote f square n is basically equivalent to applying this function twice, okay? And more generically speaking, f to the xn is basically applying this function x times, okay? One after the other. So the question is, find an x such that this thing comes out to be 2 for a given n. So the answer should be in terms of n. Maybe the answer is log n. Maybe the answer is log n. Maybe the answer is square root n. That is basically when x is equal to log n and you keep on applying it, then you reach 2. That's the question basically. I don't know which of them is the answer. Like I do know, but I don't want to tell that. But like you can consider these as different options. Yeah, just treat this as an entire question. I think it's a good exercise to do this. Question 5, let's just remove this because yeah, it's not really relevant right now. It will become more relevant when we do square root decomposition or things like that. So question 4, I think that's a good question. So you have the set of numbers which is basically equal to n by 1. Okay, floor is basically a math function which basically takes the floor of the double. So if you have, let's say, n equal 10 and you do n by 1, floor of n by 1, you basically mean floor of 10. And then if you do floor of n by 2, you basically mean floor of 5, which is again, like the floor of 10 is 10 and floor of 5 is 5. If you do floor of n by 3, it basically means floor of 3.333, which is 3. The floor basically brings it down. So it basically truncates this portion. It typecasts a double into an integer, and the way it does it is it brings the number down. It doesn't round it up, it rounds it down. That's why it's a floor. Like in a room, you have a floor and you have a ceiling, right? The ceiling is where the fan is. That's why when you do a ceiling, it brings it up. Okay. And floor of n by 4 is basically 10 by 4, 2.5, which is 2, and so on, right? You get the idea, right? And you create a set of all these things. So, okay, basically the question is, how many distinct values are there? Like, let's say n was some generic value. Let's say it's not 10. Okay, at least for this case, I can quickly show you what the answer is. Okay, so for n equal 10, the answer is basically how many distinct values are there in the set 10, 5, 3, 2, 2, 1, 1, 1, 1. Okay, if you calculate n by 7, n by 8, n by 9, n by 10, all will come out to be 1. So you have all these values, right? 10. Yeah. How many distinct values are there in this set? There is 10, there is a 5, there is a 3, there is a 2, and there is a 1. So there are 5 distinct values. Right? So basically in this set, there are 5 distinct values when n is equal to 10. My question is, for a generic n, how many distinct values does this set have? Okay, so Subrat says it's log n. Okay, I don't know. If you think it's log n, try to prove it, because I don't think the answer is log n, honestly. And like, take 2 or 3 minutes, everyone. Try to think of what the answer could be. Okay, I won't erase that effort here. But like, try to think of what the answer could be. And yeah, okay. Obviously, it's not really relevant to complexity analysis directly right now, but this thing comes out, like it comes out in some questions. Like it's not that frequent, but it's an important fact to know later on. Okay, so Anubhav has this answer of square root n. Okay, so right now what options we have are log n. Okay, but like I feel the most common guess for most of the questions, if they involve something complicated, is log n, and most of the times it works also, to be honest. Let's say the other one is login into login. Okay. Let's say we have all these options. So what I'm asking is, what's the worst case? Obviously, there can be a certain value of n for which this thing comes out to be pretty low. Let's say n is a very divisible number, n is 36 or like 24 or very divisible number. Then it might be the case that this thing like it has few distinct values. But what I'm asking for is kind of the worst case. Yeah, like it'll have at most. Obviously, it'll have at most n, but can it be better than n? So others said that it can have at most n. That's correct. Like obviously it's a set of n elements, so it can't be more than n, but maybe it's square root n, or maybe it's log into log n, or maybe it's log n. Yeah. And if anyone is has these solutions, if they want to discuss their approach or why they think it's correct, they can just either write on the chat or just unmute themselves and give their thought process. Yeah, don't be shy. I don't know why people are not unmuting themselves. Yeah, it's an interactive session. You can go unmute and actually talk with the group. Because we don't have so many people, so I think it's all right if you share your thought process. All right, so we gave a few minutes to think, and I think we should start now. Yeah. So okay, so the answer is actually square root n. All right, the way it works is, so think about what will happen when, okay, so try to think about it like this. Initially, the drop will be pretty large, like n by 1 is pretty big, then n by 2 is most likely going to be different from n, and n by 3 is going to be most likely different from n by 2, so on. When you reach square root n, this thing will roughly be equal to square root n, right? It will be roughly equal. I don't have a symbol for roughly equal, so let's use this. Okay, it'll be roughly equal to square root n. When you start going above this, think about what will happen. So, okay, notice that this function is decreasing, right? Like obviously n by 1 is greater than n by 2, which is greater than n by 3, so on. Basically, this is obviously true, right? And so on till n by square root n, and then so on till n by n, right? It's obviously a decreasing function. When you've already reached the value square root n, and you know that this value is 1, like the last value is definitely 1, we know that, common sense. How many different values can you get in this range? From when the denominator is square root n till the time the denominator becomes n, how many distinct values will you get at the output? In terms of doubles, you can get a lot, but notice that each time we are flooring the values, we are making them integers. So first we had the square root n integer, then we had some other integer, then we had some other integer. All the integers are decreasing in order and they're reaching 1. How many different integers can we get here? Square root n. That's the first idea, that this thing will only contribute square root n elements to the set. Subrat is correct in saying that they're almost equal values. That is basically the values don't decrease that sharply after this point. Like if this value is, let's say if n is, I don't know, 100, and this is square root of this is 10. So this is 100 divided by 10, which is equal to 10. The next time it will be 100 divided by 11, which will be equal to 9ish. The next time it will be 100 divided by 12, which will be equal to, I think, 9ish again. The next time it will be 100 divided by 13, which will equal to 8ish, so on. And eventually we'll get 100 divided by 50, which will equal to 2. And after some time, we'll get 100 divided by 100, which will equal to 1. So the different values that we'll get is just 10 different values, right? So beyond square root n, we'll only get 10 different values. What about the number of different values we get up till square root n? How many different values can we get here? Again, square root n, because notice that we are this set is of square root n values at most. I don't know how to explain this in simpler words, but yeah, the idea is that, okay, this element will give some value. We don't care what value it gives. It gives A, this gives B, this gives C. Okay, this gives A1, this gives A2, this gives A3, so on. And this gives A square root n minus 1. So how many values did we get in total? Square root n values, right? So from the above thing, we got square root n values. And from the below thing, like this thing also, we got square root n values. So total, we got 2 square root n values at most. Like, yeah, at most 2 square root n values. And that's basically equal to order square root n. Yeah. So, but it's an important fact to know. Like sometimes it helps to know this property. It's a very generic, it's kind of like a mathematical property, but sometimes it helps in the analysis of things in some questions. Okay. Any doubts here by anyone? Like if you have any doubts, like just unmute yourself or just put it on the chat. And like, I feel like slightly fewer people are interacting on the chat. If you have like some, if you think your doubt is lame, you can still go ahead and ask. I don't know, like because there are 22 participants on the chat, whereas we only get interaction from 4 or 5 people. That's why. Like, if you're not understanding something, just go ahead and ask. Okay, and then after this question 6 is homework. So like just think about it later. Any other doubts regarding complexity analysis by anyone? Otherwise, we can move to the problem discussion of the 2 problems. Okay, that's all. Cool. Okay, when to use amortized analysis? That's a good question. So this was an example of amortized analysis, the incrementing code that I wrote, because I think like the broad idea of amortized analysis is sometimes that you don't get to do nested loop complexity thing. Like you don't get to do the nested multiply thingy. And like sliding window algorithms are one, like sliding window algorithm, when you read about it, it's one place where you use sometimes amortized analysis. If you read about some non-linear data structures which are slightly complex, example would be splay trees, or I don't know, trees. No, maybe not trees. Okay, union find, disjoint union find, or splay trees. Then you see sometimes amortized analysis. Obviously, it's not really required to know how the analysis works. I mean, it's one thing of having a mathematical curiosity to know how the analysis works, but in comparative itself, you don't really need to always know that. Like it just works if you know how fast is each operation of union find disjoint, and then you can use that. But like I think the derivation comes from amortized analysis, and I think like it's a pretty hard derivation, to be honest. Like I haven't done it myself. I use, when are theta and omega notation used? Okay, so I use theta and omega notations are generally used by proper CS courses. As in, omega notation is generally used as a lower bound, that this certain thing cannot run faster than a certain value. Let's say you're doing, like I gave an example earlier, let's say you're doing an insertion sort. So you know that the worst case is n square. So you say the algorithm is big O of n square, and you say it's omega n. That means is that in the best case also, this algorithm will at least take n time. Omega is generally used in that sense, that even if you give it the simplest case, that is a sorted array itself, even then insertion sort will still take n steps. It won't run in one step. So that's why we say it's omega n. Theta is something of between. So what theta means, okay, like this part is slightly confusing. I'll just give it 2 minutes and people can ignore it if they want. The difference between theta and big O is generally, for example, I'll give you an example. In insertion sort, you can say the insertion sort runs in big O of n cube. And it's correct theoretically saying that, because what you're saying is that the algorithms runs faster than n cube, which is correct because it runs in n square. But you just gave an upper bound. You gave a loose upper bound. Instead of giving the tight upper bound, which is n square, you gave a loose upper bound. You gave an upper bound of n cube, or say n to the power 5. Basically a loose upper bound. That's saying big O. Theta, whereas means that this is a tight upper bound. That is, you cannot decrease from this upper bound. So if you say, so for insertion sort, saying that it's theta n cube is incorrect because it actually runs in n square at most. Like even if you pick the worst of the cases, insertion sort will run n square. So you should instead say it's theta n square. In comparative, generally most people don't care about this, because like generally people only care about the big O, or more precisely how many steps does a certain thing takes. But if you take algorithms courses in your university or some other place, then probably they cover the theta and the omega notation. But like comparative itself, it's not really relevant or useful to know this. I mean, it's a good topic in general, but yeah, not important that much from our end. Okay, so moving on, we'll cover, I think, mul3 and the other problem, right? And people can see my screen still. I'm hoping. All right. So let's go through monthly first. I think the time is right now three. Sorry, not in like okay. I'm currently staying in Singapore, so my time is like 2 or 30 minutes ahead of you guys. Time's probably 3:14, so 1:14, so 12:45 ish, and yeah, 12:45 ish. I think we'll end the session by like around 1:30 ish or 2, I guess. Yeah. So let's quickly go through the problem statement first. Consider a very long k-digit number. Okay, by very long, I actually mean it's very long because the constraint is actually 10 to the 12. So this question was set by me only by I think 2 years back or something. And the first two digits of the number are given, which is D0 and D1. And you're given a formula to create the next number and so on. The formula is quite simple. It's basically take the sum of all the preceding digits. So Di is the sum of all the preceding digits. That is the digits that came before the ith digit, and you modulo it under 10. Because it's a digit, so it can't be like 15 or 37. It has to be a number between 0 to 9. So you modulate it under 10. Formally, you can write that di is basically this thing, right? And you have to determine if, like, you have to basically check if the number created this way, which is basically this number, is it a multiple of 3 or not? Okay, so firstly, yeah, that's the entire question, right? And okay, you're given that D0, which is the most significant digit, is non-zero digit, and D1 can be 0. D0 basically goes from 1 to 9, so it can't be a 0. Okay, so this is the question. I'll so I will connect my give me a moment. I'll connect my iPad because like firstly we'll like for the next 10 minutes or so, we'll just go through the rough derivation of the entire thing, like what an algorithm should be, blah blah blah, and I'll just try to derive everything. Then we can go through the say sorry. Yep. After the derivation, we can go through the implementation part. Please explain the question again. Okay. Okay, so the question was, I switched to my iPad, so I'll just explain it here. So you have a digit D0 and a digit D1. This can range from 1 to 9. This can range from 0 to 9. You're given both of these digits and you're given K. You're given a method to create all the digits. So the number N will be basically equal to D0, D1 to dk minus 1. Here, what I'm meaning is it's not a multiplication. It's more like I'm sorry, I had a call. Yeah. So here actually this is the first digit of N, this is the second digit and so on. This is the kth digit. It's not multiplication of the digits. It's more like how you represent it in base 10. All right. And the way to create DI is you sum up all the preceding digits. That is, so let's say here is a DI. So the way to create it is you take the sum of all the digits before it and you modulo this by 10. That's how you create DI. So Nikita, is the question clear? If it's still not clear, you can just open the web page. I mean, I can. Yeah. Like we can just go through the problem statement here. Okay, anyways, let's move forward. So notice what the values, like let's try to come up. So, okay, first thing is that when you see the question, I think the instant thing that comes up is that how do we test whether n is a multiple of 3 or not, right? How do we test whether n is a multiple of 3 or not? So most people in high school have done this, that that multiplicity test for a 3 is basically take the sum of the digits and check if the sum of the digits is multiple of 3 or not. So what we want to retrieve is sum of all the digits. If we can get this value, then we are done. We can just check whether it's divisible by 3 or not. And yeah, right. So that's the first step that you should think of when you see this question. Okay, if you didn't know this fact that sum of the digits, if the sum of the digits is a multiple of 3, then the number is divisible by 3. If you didn't know this fact, you can Google it up and like, yeah, I don't know how to explain this. It's a pretty known fact generally. And there should be a proof online, or like I can share a proof if someone wants, of why this thing is equivalent to saying that n is a multiple of 3. Like if this thing works to be divisible by 3, then n is a multiple of 3. Okay, so we want to recover this thing, right? Now, say the k was small, say the k was actually 10 to the 6 or something. In this question, actually k is pretty big. It's actually 10 to the 12. But if it was small, you could have just created all the digits. You could have just done something like sum equals d0 plus d1, and then total, like just keep on adding the sum inside the total, and in each time, in each iteration, update the sum, right? Like something like this roughly. Like you just double the sum each time. Basically just create all the digits manually and like create all the actual digits manually and then get the sum and check. That would have been simple had k been small, but k is not small. Because k is not small, this algorithm, that's the slow algorithm, it works in order k, which won't work because order k is actually order 10 to the 12. Okay, and just to give you an idea of how slow this algorithm is, think about this. You can do 10 to the power 8 operations in 1 second. How many seconds will it take you to do 10 to the power 12 operations? It will take you 10,000 seconds, which is roughly 10,000 by 60 minutes, which is roughly 1,000 by 6. So I don't know, 200-ish minutes, which is roughly 3 hours. So for k as big as 10 to the 12, this thing will roughly take 3 hours, right? So you can't do that. Like your judge only gives you 1 second or 3 seconds at most. You can't run such a big thing. The next idea that comes up is like, okay, basically so we want to recover this thing somehow, right? The sum of all the digits, but we don't want to create all the digits. That's the idea. We don't want to create all the digits, but we want to get this value still somehow fast. So the idea is you create D2, which is basically D0 plus D1 mod 10, right? Then you try to figure out what D3 is. So D3 is D0 plus D1 plus D2 mod 10, which is equal to D0 plus D1 plus D0 plus D1 mod 10. So I'm just replacing D2 here with this expression, right? And I get this entire thing. This is actually a mod, right? I get this expression. Which is actually D0 mod 10 plus D1 mod 10. Okay, let's not write it like this actually. Yeah, so if you have something like a plus b mod x, you can write it as a mod x plus b mod x whole mod x. It's equivalent. Like these are just some properties of modular arithmetic. I'm not explicitly covering them, but this is equivalent. Okay, so you can write this as D0 mod 10 plus D1 mod 10. Oh, shit. Plus, when you open this up, you can again write this as D0 mod 10 plus D1 mod 10. Okay, another property that you have is a mod x whole mod x again is equal to a mod x. That is, taking the modulo under the same thing twice is still the same thing. So here, when we take the D0 out, it's getting modded twice by this mod 10 and this mod 10, both the mod 10. And this D1 is also getting modded twice, right? So you get this entire expression, which is equal to 2 times D0 plus D1 whole mod 10. The way it works is you club both the D0s. So you say 2 times D0 mod 10, and you club both the D1s. And since the entire thing is under mod 10, you can just do the entire expression here and put a mod 10 outside, right? So D3 came out to be this thing, which is like, I did a lot of math here, but like it wasn't really required. What will D4 come out to be? It will come out to be D0 plus D1 plus D2 plus D3 whole mod 10. Okay, now let's start writing D0 plus D1 as S for simplicity, because we always see that they come together, right? So if we start writing them like this, it'll like the thing will become simpler. So D2 will be S mod 10. D3 we just calculated is 2S mod 10, right here. And D0 plus D1 is S. D4 will be, okay, so here D4 will, what will it come out to be? We can club these as S. We can say we already calculated D2 as 2S. Sorry, D2 was actually S. Yeah, D2 was here and it was actually S. And D3 was actually 2S and whole mod 10. So this is S plus 2S, which is 4S, right? 4S mod 10. So D4 came out to be 4S mod 10. Right? And so on. So D5 will actually be 8S mod 10. The way it works out is you add the previous guy, you add the previous guy, you add the previous guy, and you add D0 plus D1, which is equal to S. So you add S, and another S, another 2S, another 4S, which is 8S, right? Now, when you calculate D6, you'll get 16S mod 10. But notice that 16S mod 10 can be simplified. It can be simplified as saying 16 mod 10 times S mod 10, which is equal to 6 S mod 10. Okay, so D6 is 6X mod 10. And let's calculate another few values. Let's calculate D7. So D7 will be all the sum of the previous guys. So 6S, 8S. Okay, instead of using 6S, just try to use 16S because you're anyways doing a modulo 10 later. So just do 16 plus 8 plus 4 plus 2 plus 1 plus 1. You can notice that this is 32 because it's like all the powers of 2 and another S additional. So it's 32S mod 10, which when you simplify 32 under modulo 10 is actually 2 because it's 32 is actually 10 times 3 plus 2. So it's 2. So you get 2S mod 10, right? And so on. Now the pattern here that comes out is that generically speaking, dk will be equal to something of the sort 2 to the k minus 2 S mod 10. Like if you just try to work this out for further values, you'll get this pattern that dk is always equal to 2 to the power k minus 2 S mod 10. It's not really even a pattern. It's more like saying dk is basically the sum of all the previous guys. And we know the sum of previous guys is kind of like S plus 2S up to 2 to the k minus 3, which comes out to be 2 to the k minus 2 times S. That's how the like expansion works. So that's true for all k greater equal to, right? This thing is true. Now modulos have this property that if you're working under the field modulo P and you have A, then you have 2A, then you have 3A under modulo P, all of them. Here P is not necessarily prime. This thing will start looping after some time. This property is always true for any modulo, that this thing starts looping after some time, starts cycling. So in this case, we have the value Okay, sorry, my bad. My bad. It's actually, the statement is actually this. If you have A, then you have 2A, then you have 4A. So not actually A, more like if you have A, then you have A square, then you have A cube, and so on. Here, what the value of A that we are using is 2. So we have 2, then we have 4, then we have 8, then we have 16, and so on, 2 to the x more generically. All of them are under modulo 10. Then this values will start looping after some time. Is this clear? I mean, it's not really clear why it does this happen, but it does happen. In this case, you can see that it's 2, then it's 4, then it's 8, then 16 actually becomes 6. So in 16, we actually drop the 1. 32 actually becomes 2 because you're under modulo 10. And we notice the loop happen. 64 is actually 4. So you can notice that 2486 is again going to be repeated here. Can anyone give a reasoning on why this works? Like, why does this looping structure happen? It's not that complicated. Like, anyone on the chat wants to give it a try, or just unmute yourself and give it a try. Like, why does this looping thing happens? Okay, so I'll give the idea here quickly. The reason why the loopy thing happens is, let's say, okay, how many values can come here? Like, each value is definitely between 0 to 9, right? Yeah, mom is somewhat correct. That we keep multiplying by 2 and use only the first bit. So the idea is that each value is from 0 to 9. So, like, once you start going, you'll definitely, after 9 steps or after 10 steps, definitely repeat some value. Let's say the first value is A1, the next value is A2, the next value is A3, so on, up till A10. Definitely A11 will match to one of the existing values, right? Because there are only 0 to 9 distinct numbers under modulo 10. So if all these guys are distinct, A11 should definitely match, right? Maybe the match happened somewhere before, but like at the 11th point, definitely a match should come. Maybe the match happened here only, or I don't know. But let's say the match happened at A11. Okay. So notice what these values actually are. A1 is actually A to the 1, A2 is actually A square, A cube, so on up till A to the 11. And let's say A11 is equal to A3 under modulo 10 or whatever, modulo P, generically, right? Now, what will A12 be equal to? A12 will be equal to A11 times A, right? Which is A cube times A, which is A to the 4. Because A11 is same as A3, we just showed here. And we are multiplying by another A, so it's A4. So A12 will be equal to A4, A13 will similarly be equal to A5, and so on. So notice this 3 to 11 cycle, like, okay, sorry, my bad. This 3 to 10 thing is going to get repeated here. This cycle, let's label it C, will again get repeated here. Does everyone get this? Basically, the first point that you find that a value matches some previous value, after that point, it's easy to see why the same things repeat. Because of the derivation, like A to the 12 is basically A to the 4 after this point. I'm just giving an example here. But that's how the proof works, that why it always cycles back. It might be the case, obviously, here the cycle starts from A cube. It doesn't start from A1 or A2. It's not necessary that it starts from A1 or A2. But once the cyclic structure starts, it keeps on going in the same cycle again and again. Any doubts here? This is like a modular arithmetic thing, but like people should know this if they're trying to solve this question. So in this question, we got this expression, right? And we saw that it cycles like this. So the first value was D0 plus D1, which is equal to S. The next value was D2, which is equal to S. The next value was D3, which is equal to 2S. Then D4, which is 4S. Then D5, which is 8S. Then D6, which is 6S. And then we find a loop of this thing here. So D7 is again 2S. D8 is again 4S. and then 8s, then 6s, and so on, right? So we have this loopy structure, but obviously the loop starts from D3. It doesn't start from D2 or D1. Like we don't care about that, to be honest, but that's how it works. Okay. Any doubts here? All right, cool. So we don't have any doubts. So like how the net algorithm will work is we'll say like if this thing goes till dk minus 1. So we'll try to figure out this thing. We'll say this is D0, this is D1, this is D2. And then we have groups of 4 guys, right? Each time we have groups of 4 guys. So probably a dk minus 1 ends somewhere here. So we'll try to find out how many cycles are there up till dk minus 1. In this case, let's say there are 3 cycles, cycle 1, cycle 2, cycle 3. So up till dk minus 1, like what will be the total sum of all the di's from 0 to k minus 1? It will be equal to the first 3 terms, that is d0 plus d1 plus d2, plus the sum of the cycle and the number of times the cycle comes, right? So the sum of the cycle is basically, this is what 2s, this is what 4s, this is what 8s, this is what 6s. So the sum of the cycle is 2s plus 4s plus 8s plus 6s, which is 2s plus 4s. So 6s plus 8x, 14s plus 6s, 20s, something of this sort, right? Roughly. And like how many times the cycle comes, plus the leftover. What leftover I mean is, it might be that this part, like this dk minus 1 is part of a cycle. So you have to add the first term, the second term, the third term. Maybe the cycle doesn't get completed here. So we have to add these terms separately. Right? So that's the leftover here. So is the formula clear? Like how is this thing coming up here? All right. Cool. And okay, when I said 20s here, I was actually slightly incorrect because D3 is equal to 2s mod 10. D4 is equal to 4s mod 10. D5 is equal to 8s mod 10. D6 is equal to 6s mod 10. Now, when we are taking the sum of digits here, we are not taking them under modulo 10. So we can't just say that take 2s plus 4s plus 8s plus 6s 20s mod 10, which is equal to 0. You can't do that because here we are not taking the sum under modulo 10. We are just taking the sum of all the digits, right? And then we want to check whether it's divisible by 3 or not. So it's a very slight detail, but it's important to understand that you're just taking the sum of the digits. You're not taking the sum of the digits under modulo 10. An example would be something like this. 452, let's say the number is this. Taking the sum of digits means you're taking 4 plus 5 plus 2, which is, sorry, 453, let's say. So taking the sum of digits is basically 4 plus 5 plus 3, which is 12. Taking the sum of digits under modulo 10 means it's 4 plus 5 plus 3 mod 10, which is 2. Notice this thing gives you an incorrect answer because 2 is actually not divisible by 3, but 12 is actually divisible by 3. And 453 is actually divisible by 3. So you don't want to calculate this thing. You don't want to calculate it under modulo 10. You want to calculate the actual value. So that's why you take like the expression for C here in this code will be 2s mod 10 plus 4s mod 10 plus 8s mod 10 plus 6s mod 10. I won't recommend you to try to simplify this expression. Just keep this expression as it is. Don't try to make it 20s or whatever. Because otherwise you'll put a mod 10 outside it. You can't write it like this. You can't write some stuff inside and then do a mod 10 outside. Is this clear? So will there be a change in the number of coming cycles? Not really. I mean, because of this explanation or something, there is no change in the number of cycles. And The number of cycles actually comes out to be k minus 3 by 4 as far as I remember from the question. The idea was that you remove these three terms, right? So you have k elements up from 0th up till kth, k minus 1th. You have k elements, and the first three elements don't contribute. Sorry. Give me one. I think I lost the note. Should we have this? I don't know where you're working right now. Yeah, so okay. Sorry. Yep. So we have k terms here from 0 to k minus 1. And the first three terms do not belong to any cycle. So we remove them. So just think we have k minus 3 terms starting from 3 up till k minus 1. And so the number of cycles that will be there is basically k minus 3 by 4 floored. Yeah. So the floor symbol is this one that we were using earlier. We were trying to use this thing, right? On the Sublime text, floor n by I or n by 1, whatever. This is actually written as this thing in mathematical notation. You use this downward going brackets, basically. So the number of cycles is k by 3 by 4, right? So is this part clear? Like I expressed C here as this expression and I expressed number of cycles here. And we'll get to the leftover part during inside the code of how to calculate the leftover. Any questions? Let's see. We have. So if you just guys can see, I think hopefully my font is not that terrible. Yep. So we first taken K, then D0, then D1. So hash define is basically used as a shortcut to write, like avoid writing long again. And then we can say long cycles. So C, which was our sum basically. Okay, first let's create int S equals D0 plus D1. Then say cycle sum was 2 times S mod 10 plus 4 times S mod 10 plus 8 times S mod 10 plus 6 times S mod 10. Then we say int num cycles is equal to. Okay, so this should be actually a long. That yeah, we need to be careful about this because the reason is because k is long. So if you're manipulating something on k, then it should be a long, right? And tot denotes the total that we get. So it'll basically be okay. Firstly, we can handle some cases of the fact if k is less than equal to, or do we need to handle these cases? Yeah, we need to handle these cases separately. So then the total will be let's see. What's the smallest value of k possible? Okay, so k actually starts from 2 itself, right? So k equals 2. Then we can say that total will be equal to s plus s because it will be d0 plus d1 plus d2, and d2 we know is s, right? So it will be 2 times s. That's it. Otherwise, we can say total will be equal to 2s plus, okay, I'm adding 2s because it's basically contributing d0 plus d1 plus d2. Then I'm adding c into 1ll into num cycles. I use 1ll here because c is an integer. So 1ll basically typecasts it to a long. Here num cycles is a long, so it doesn't matter. But let's say this was an integer. If this was x, where x is an integer, and you still want the product to be a long, you can do into 1ll. That's a trick that a lot of people use. Okay. And then we calculate the leftover, right? So how do we calculate the leftover? We can make cases also. If you think it's simpler. Or let's not make cases actually. Let's see leftover is basically how much. So it's more like saying k minus 3 by 4. K minus 3 minus num cycles into 4. Right? That much will be the leftover. 4. For k equal to, it shouldn't only be d0 plus d1. Okay, my bad. Maybe I'm incorrect. Yeah, sorry, my bad. Shit. Yeah, sorry, because it's only, okay, it's less than k. Yeah. So it's up to 1. Otherwise, it's basically 2 times s, because we are covering d0, d1, d2 definitely. And then we are covering c times number of cycles. And after covering all the cycles, we are covering the leftover. When should we use long and when long? Okay, generally I would recommend never to use long. Just don't use long. That's the simple case. Like either use an integer or a long. That's it. So this is the leftover. Now I think we can do something like this. And we can keep on doing. Yep. So here the idea is, okay, let's put a value of k just to get a feel of it, how the algorithm works. If k is 2, we get s. If k is, let's say, 10, okay? So if k is 10, we are trying to calculate d0, d1 up to d9, right? So the 2s contributes 0, 1, and 2. Then number of cycles will be k minus 3 by 4 and the floor of it. So it will be 10 minus 3, 7, 7 divided by 4, 1, right? So that will be the number of cycles, and c will be some constant, we don't care. So notice when we add both these things, what have we added? We have added the 0th term, the 2nd term, the 3rd term, the 4th term, the 5th term, the 6th term. That's it. We haven't added any more terms because 3, 4, 5, 6 is forming one cycle. And here we said that we are adding only one cycle. Now, what do we need to add? We need to add 7, 8, and 9, right? So we try to calculate the leftover. The leftover is basically how much? So k is 10, 10 minus 3, 7. 7 minus, how many cycles do we have? 1 into 4. So 3. So basically, that's how much the modulo is left. That's why I calculated it in such a way, k minus 3 minus number of cycles into 4. So 3 terms are left to be added. And we know that the cyclic structure starts from 2s, then 4s, then 8s, then 6s, right? So we can simply say that okay, so since the leftover is 3 here, I'm adding from 1 to leftover, and I'm adding each term one by one. And I know that the leftover is definitely less than 4. Because if it's greater than 4, then we could just add one more cycle. So yeah, like this loop will definitely be order 3 at most. Kind of like saying order less than equal 4. So it's pretty fast loop. Although there is a loop, but you don't really care about loop. So in total, we'll add p into s, and p starts with 2 because the first term in the cyclic structure is 2s. And we keep on multiplying the p by itself, by 2, sorry, under modulo 10. So that's why we get 2s first time, then 4s, then next time we'll get 8s. And last time we'll get 16s, but technically it's under modulo 10, so we'll get 6. And that's why p will be 6 the last time, and we'll add 6s. Okay, is this portion clear? Once we get this thing, we can just, I think, we can just test. Another, I don't know, trick or whatever is that use \n compared to endels because it's faster. I mean, a lot of people would be knowing this before also, but yeah, that's one thing that most people do use. like use \n instead of indels because it doesn't require buffer flush in the C++. And I think this is pretty much it. Now, okay, like the benefit of doing this kind of like compiling structure that is basically opening Vim and then compiling from the terminal is that you can copy paste this portion in a text file, right? And then you can compile your thing. The last part is basically adding the flag of allowing C++11 features. And then you can do this, which is basically input redirection. I don't know if all of you know this, but okay, Subrat asks, is it true that printf is faster than cin? I personally don't think so. Like, I think a lot of times when people, I'll just show this. Wait a second. Sometimes people add these two lines and then it pretty much makes both the things similar. I think if you add these three lines, simple base. Yep, these three lines, then it's pretty much the same as scanf printer. Like I have never seen this thing TLEing where a scanf printer passing. Yeah, but I mean, obviously \n's are much faster than indels. So definitely use \n's. Okay, \n's only come into play when \n's only like they affect your complexity significantly only when you're printing a lot of stuff. In this question, the number of test cases is 1,000. So you're still printing very few lines. You're just printing 1,000 lines. But if this T was 10 to the power 5 or 10 to the power 6, it would have actually made a big difference because you would have printed a lot of lines and that time \n actually makes a big difference. Okay, the difference in \n with endel is that endel in cout forces a buffer flush. So if you read about something like file IO, like how does C++ read in stuff from the standard input and print out stuff from the standard output, there is a flush concept and \n basically avoids that flush. And you don't need that flush for online judges, really. You just need it at the end. So even if you do a fflush std out at the end, it's all right. Oh, you asked for the 3 lines above, sorry. Okay. I don't really know what they exactly mean, but like the broad idea that I've got from the documentation is that they're basically flags that you enable or disable. What they do is, okay, in generic C++, what happens is when you do a cin or a scanf and you mix those statements, let's say you did a scanf first and then a cin or whatever, and you mix those statements. So you're taking an input from both the sides. Sometimes you're cinning stuff, sometimes you're scanf using scanf. If you're doing both the things together, like one after the other, what the library of cin or scanf does is whenever it sees a scanf, it waits and checks if there is a cin before me or not. Basically, they need to collaborate with one another, the cin and the scanf. When you write these 3 lines, or at least for these 2 lines, when you say cin.title and sync with stdio, you're saying disable the sync. So now if you run a scanf, like let's say after taking, okay, let's say example, after taking D0, we do scanf %D and DO. Let's say we do this. This thing won't actually work correctly right now if you have enabled these flags. If you disable these flags, then this thing will work. But when you've enabled these flags, this thing doesn't work correctly because these flags explicitly tell the compiler to, in some sense, ignore the scanfs. I'm not really sure if they ignore it, but it's more like don't try to put them together when you enable these flags, when you put these 3 flags. And similarly for cout and printfs can't get mixed. So when you put those flags, you're basically saying that I'm committing myself to cins and couts. I will only use cins and couts in my code. I won't use scanners and printfs. And that's why the compiler is able to optimize that portion, because it knows that your code won't have scanners or printfs in between. At least that's what I got from the documentation or like 1 or 2 blogs that I read about this, like why this optimization works actually. Yes, so when the sync is off, cin and getline actually, yeah, if you mix stuff together, it actually breaks things. Okay, interesting. So we are getting a bug here. I honestly don't know what it is, but let's see. So for the first case, we are getting a no. For the second case, we are getting a yes. Oh, sorry, we are getting a no again. We are not getting a yes. So, okay. Let's try to print out some stuff. Let's try to print out C and num cycles. Yeah, I honestly don't know the bug. Like if anyone can figure it out, be my guest. Okay, so in the second case, C is 20 and the number of cycles are 2. Wait a second. Why is C 20? So S is coming out to be D0 plus D1, which is, I think, 9 here, right? If I'm not mistaken, it's 9. Let's print out S also. Yeah, so S is 9. And then C comes out to be, okay, 2 times S, that's 18. I think we have the incorrect value of C. But I don't know. Technically, it should be, okay. I think it's a bracketing issue. I think it's like the entire thing is getting modulo 10, whereas we don't want that. So in the sum, we're getting the good value, 9. But like here, this will be 9 into 2, 18. And here it will be, no, 9 into 4, 36. Okay, sorry, 9 into 2, 18, but it only contributes 8. Then 9 into 4, 36. Huh, but it contributes 6, right? I don't know why I'm getting the C as incorrect. It doesn't seem obvious. 2 times S mod 10 plus 4 times S mod 10 plus 8 times S mod 10 plus 6 times S mod 10. Let's try 13, 8, 1. Anyone got any ideas? Like why is the C? I feel the C is incorrect. Like S here came out to be 9. But C here should have been, I don't know, 18 mod 10, which is 8 plus 6 plus 2 plus 6 into 10, 54, 4, which is, oh, which is correct. Okay, sorry, 14, 16, 20. Okay, sure, that's correct. Okay, then number of cycles comes out to be 2. Is that correct? I think that's correct because we have 0, 1, 2 as one chunk. Then we have 3 to 6 as one chunk. Then we have 7 to 10 as one chunk. And then 11, 12, 13 will come as like the remaining leftover part, right? So the number of cycles is 3 and 6 and 7 and 10. So there are 2 cycles. Yeah, so that's correct. Then we have, so we have this thing, which is summing up D0 plus D1 plus D2. Okay. So I think here is one bug. So D0 plus D1 actually contributes S. D2 actually doesn't contribute S, it contributes S mod 10 because the value of D2 is actually S mod 10, right? And then we say C into number of cycles, and then we do the leftover thinking. Okay, still doesn't work. Interesting. So we got the values correct till here. Now the total will become, what will be the value total? The sum is 9 plus 9 plus number of cycles is 2, and each cycle is contributing 20. So 18 plus 40, which is 58, right? And the leftover is 3. And each time we are adding 2s, 4s, 8s. So we're adding 2s mod 10, which is how much? 8 plus 6 plus 2. So I think we're adding 16 here. Yeah, and we already had 58. So 58 plus 16, 68, 74. Huh. Okay, I'm confused now. Oh, okay. I think I might recognize the bug. So one issue here is I actually don't have to count in 13th term because k is 13. So we technically have to only go till the 12th term, right? Yeah. And the leftover should actually come out to be 2, I guess. Let's see what the leftover is. It's 13 minus 3, so 10, minus number of cycles, so 2 into 8, 4. So that's 2. So the leftover is actually 2. And so this thing will be actually 14. This thing will be 58, 68, 72. Okay, so it should technically be divisible by 3. I don't know why we don't get it. So, okay, let's try to print out something there. I think this should be easy. So we'll print out the tot before adding the leftover. We expect it to be 58. And we'll print out the tot after adding the leftover. We expect it to be 72. Let's try to see where the bug is. So it came out 58 and then it came out 112. So the part before it was correct. Here we made some bug, some stupid bug. Okay, my bad. The leftover is actually, there are 2 terms that we need to add. The first term is, I thought it's 2 times s mod 10. Oh, okay. Oh. So it's actually 2 times s mod 10, not just 2 times s, because we are adding a digit and that digit is under modulo 10. Yeah, so that was the issue, I guess. I think this should fix it. Yep. So, okay, one more thing I wanted to show was that basically this creating input.txt is beneficial in this sense that I'm able to debug very fast because I don't have to constantly do this, then copy paste from my clipboard the entire test case or stuff like that. I feel sometimes in code blocks, people have this lag of like wasting 5 or 10 seconds whenever they're debugging because they're constantly rectifying that issue of like copy pasting things. And, so we have this code. I think it works. Let's. I haven't actually used CodeChef. Okay, this is embarrassing. Oh, I haven't used CodeChef in a very long time, so I don't know really how this works. I thought I attached the file. Does someone know like why isn't the attached working? I mean, I go to open file and then I click on a.cpp, then I assume that the file is attached, but looks like it's not. I think it's open. All right, yeah. So this works, right? So this was the code where we had like one if condition and then the else, and we had the leftover thing. Now let's try to do the other problem. I think we'll go through this one much quicker because I think we only want to do it like, I think we only want to extend it like by 15 minutes more. Yeah, so let's go through the problem quickly. So you're given a smartphone app, you have a list of potential customers, blah, blah, blah. So each customer has a budget and he'll only buy the app if the app is less than equal his budget. You want to fix the price of the app such that you get maximum revenue, right? So, okay. Firstly, like fixing the budget very low is also not optimal because even though a lot of people will buy it because like the price of the app is smaller than all of the people's budget. Let's say you fix the price of the app as 1, then everyone will buy it, correct? But you'll only make 1 profit from each guy. Similarly, thinking that you can set the price to be maximum, let's say set the price to be 100, but only few people will buy it, then also it's not optimal. So you want some good value in between, right? Now, one of the hints that I gave earlier was, let's say these are the values. So the things look like this, and let's just sort this array. So it looks like 14, 20, 30, 53. These are the 4 guys with their budgets, right? If you set the value of the app to be 20, then how much profit will you make? You'll get 3 guys to be able to buy the app, right? 20, the guy 20 will buy, the guy 30 will buy, the guy 53 will buy. So 20 times 3. So you'll make 60 profit. Had the app been of price 19, how much profit would you have made? Still, those 3 guys would have bought it because still these 3 guys are bigger than 19. But you would have made 19 times 3, which is obviously less than 20 times 3 because 19 is smaller than 20. So if the same number of people are going to buy your app, then pick the price which is better. Right? If at price X, 5 people buy it, and if at price Y, 5 people buy it, then pick the one which is bigger. If X is greater than Y, pick X. Like obviously X is better. Right? That's the intuition. And here another, like the last exploit of the problem is that, so what this ensures is that you don't have to try all the values. Obviously in this question, you can see, okay, so there is no, okay, there are constraints given, right? So the maximum value of n is 5 to 10 to the power 5, and each customer's budget is very big. Like it can go up to 10 to the power 8. So you can't try every possible value of the app, which can go from 1 to 10 to the power 8. You don't want to try this because this thing itself will be order 10 to the power 8 multiplied by how much time will it take you to know how many people will buy your app. That is how many elements are greater equal value in array. So this will be the total complexity, right? And even though you can do the stuff fast, but this is still barely within your time limit. So it might really, like if your constant is too high, you might take 2.5 seconds instead of 2 seconds or something of that sort. Here the time limit is actually 1 second. So I think like trying out this thing is pretty risky for this kind of problem. So like this statement, what this provided us was that you don't need to try really all the candidate solutions. You only need to try the values present. Like obviously trying out 19 here is stupid because if you try the price 19, 3 people will buy it. But if you try the price 20, still 3 people will buy it. And to, like you'll obviously make more money when you put it at 20. Similarly, trying out 25 or 26 is stupid. You could just try 30 because at the price 26, only 2 people will buy it. But at the price of 30, also 2 people will buy it. So you only need to try out these values as your possible answers. That's the main exploit of the problem. So your candidate solutions are order n. So earlier we were trying out, like we thought that we'll try out 10 to the power 8 values, but now we know that we only need to try out n values, right? And also, once you've sorted the array, it's easy to see how many people will profit from you. If you fix the value 20, 3 people will profit from you because there are 3 elements ahead of 20. If you fix the value at 30, 2 people will profit. Like you'll profit from 2 people. 2 people will buy your app because there are 2 elements ahead of 20. So that's pretty much the logic of the problem. I'll just get into the coding aspect. So in the first integer, he gives you n, then he gives you the array. Then you just sort the array. Then you go from. Okay, one thing to notice, how big can the answer be? So the price of the app times the number of people. The price of the app can be 10 to the power 8 at most, and the number of people are 10 to the power 5, like 5 into 10 to the power 5. So like if you multiply both these values, you see that it's at most 5 into 10 to the power 13. So it should be a long. Right. Also, the size of the MRA is like fixing it to be 10 to the power 6, although it's only required to be 5 into 10 to the power 5. And then we say, right, AI is the price that we are fixing it. And N minus I are the number of guys that are going to buy at this price. And the sort was there just to sort them in increasing order. I hope everyone knows why what's the syntax of the function sort. So here, because we're just printing one answer, you can use end. It doesn't really matter. And also notice that here n minus I is an integer, AI is an integer. So to avoid an overflow, you need to add a 1 LL. When you add a 1 LL in between, when this thing n minus I gets multiplied by 1 LL, it gets typecasted to a long. And then when a long thing, that is this entire thing, gets multiplied to AI, it's basically a long multiplied by an integer, and the integer gets typecasted to another long. That's why this thing works. See this thing. Yep, so it came out to be 60. And this thing. And came out to be 19. Is there any problem or waste without making a huge array that is empty or no? Mohammed asks a very good question. Like I've seen a lot of people do precise calculations here. It generally doesn't matter, honestly. It's just that, okay, declaring this array itself takes 10 to the power 6 steps. It doesn't take 5 into 10 to the power 5 steps. So obviously I wasted some time in declaring extra elements of the array, because like the declaration itself, line 8 will itself take 10 to the power 6 steps. So that's a flaw in my code currently. But it's just like you could do this, but if you think it's fast, like, okay, you could do this because that's the actual constraint of the problem. But if you think it's faster to write this, then just use that. Yes, that time does count. So if you're declaring, let's say you're declaring a very huge array here, 1A9 plus 5, maybe you can declare it barely because it's like, maybe it's barely within 1 GB. I don't think it's within 1 GB, but let's say it is within 1 GB, let's say. Then yes, you can declare it because CodeChef does allow memory constraint up to 1 GB for some problems. But the issue would be that declaring the array itself will take a lot of time. And that time is counted in the judging time. So in the judging time, generally how you think about it is the compile time is not counted. That is basically saying this command. How much time does this command take to generate a.exe? This is a.exe that I'm trying to run. So the time that this command takes to generate a.exe, it might be 5 seconds, that might be 2 seconds. This time, the compilation time, which is known as, this is not counted by the online judges, but the execution time, which is basically taking this thing and giving it input and then hoping for the, like waiting for the output, that time is counted. And both the things, giving it input, which is basically the scanf, the whatever part, and the printing out stuff, printf and whatever part. So that thing was actually part of the execution time. Declaring a vector or declaring an array is actually part of execution time. So is declaring a vector that is sized accordingly every test case is actually worse than your code? No, it's not. It's actually better. Like in my code, I'm just declaring an array, a very big array every time. So even if n comes out to be 5, I'll still take 10 to the power 6 plus 5 time. But if, like, even if n is small, but if you declare a vector here itself and then put all the stuff inside the vector, it's faster. The thing is that most of the times this doesn't matter, like this time, but it's generally just more convenient. Okay, sorry. So Mohammed was asking that is using a vector here better than an array? And like, because vector will be dynamically sized here. It is generally better in terms of time complexity. It's just that it's very negligible. Like I haven't seen ever that thing actually benefits you. And just writing something in global, I personally find it more convenient for me, myself. Adra player asks, will using a vector be beneficial? in this case, it's not really a make or break because what I said, like, because here this much space allocating order and space is anyways too trivial. Like you don't really care because it's fast also and it's not a lot of space also. But at other times, example, you're creating an adjacency list, which is a very common thing you create for graph data structures or like for graph algorithms. At that time, like creating an adjacency list definitely does require vectors because you can't allocate that much memory. Like if you use trivial arrays, you'll allocate too much memory. In this question itself, I don't think using vectors makes like gives you a very big advantage. As in, you can use any of the two in this particular question. And I just personally prefer to use arrays instead of vectors. So I think that's pretty much it. Like hopefully it is easy. And like if you guys have any other questions, just like ask on the chat, and or otherwise we can like just start with the end of the discussion. Okay, this is taking much longer than expected. Don't know why. I don't know. This I thought this is a pretty simple code. Okay, cool. It worked. So I don't know. Maybe the judge was slightly slow that time. But yeah, that's pretty much it for this session.